multiple multiples. So in this question, we're given an alphabet that's just 0 and 1. And then we also have this language C3, which is just the set of all strings that are binary numbers that are also multiples of 3. And then we're asked to show that C3 is regular. So the first thing that you should be thinking of when you see that we're trying to show that C3 is regular is we just want to show that there's a DFA that exists that will recognize C3. And then if we can show that this DFA exists, then C3 is necessarily regular. So before we do that, I just want to go over a few examples of what is in C3 and what's not in C3. So, we have 0 first. 0 is a multiple of 3. We have 1, 1, which is 3 in binary. That's obviously a multiple of 3. We have 1, 0, 0, which is 4 in binary, which is not a multiple of 3. But I think the most interesting one is epsilon, which, for convenience sake, I'm just going to say that this is in C3. And this just makes it a little bit easier to construct the DFA later on. And also intuitively, you can kind of just think empty string, basically 0, also a multiple of 3, and everything will work out fine. So now I just want to start looking at this language over here, and hopefully we can go from this language to start thinking about what types of states and what types of transitions we need to actually construct this DFA. And to try to build this intuition a little bit, I'm going to show you another language, which is the same thing, it's just worded a little bit differently. And what I've changed is I've changed multiple of 3 to 0 mod 3. And hopefully this kind of is a little bit more intuitive to think about. And what you might notice is 0 mod 3 is very suggestive because you only have 3 possible ways to have a number mod 3. You have 0 mod 3, you have 1 mod 3, then you also have 2 mod 3. So maybe we can take this 0, 1, and 2 mod 3 and then turn these into the states of our DFA. So I'm going to write this out here. You'll see that all integers will fall into either 0, 1, or 2 mod 3. So you have 0, 1, 2, 3, all of these integers down here. And I'm also going to label each of these with Q0, Q1, and Q2. And then hopefully we can take these labels Q0, Q1, and Q2, and then as we go through a string, character by character by character, somehow we can construct some sort of DFA that will let us keep track of the modness of the string as we read through it character by character. And I'm going to formalize this a little bit just by stating this property, which is at every point in a string, when we're reading a string character by character, any string corresponding to a number omega should always end on state qi if omega is congruent to I mod 3. So basically, when we're reading through a string, we always want our string to be in the state that it's mod 3 of. So if we read in 1, 0, 0, which is 4, we want that to be in Q1 since it's 1 mod 3. And then if we go from this property, ideally we can find some sort of way to make some sort of transition function that will satisfy this property. And that's what we're going to do over here. So to gain some intuition about how we want to construct this transition function, I'm going to show a quick example, which is just 1, 1, 0, 0, 1, 1. And in binary, that's represented as 27. And since 27 is a multiple of 3, we want this to be accepting. And we also want this to end on Q0 since it's 0 mod 3. So let's start off with just epsilon, since epsilon is what you start off with since you have no string that you've read in so far. And epsilon's just going to start off with Q0 because epsilon is basically 0 mod 3. And then we read in our first number, which is 1. And 1 in binary is also just 1. And that brings us to Q1 since 1 is 1 mod 3. Then we read in our second one, which is going to bring us to 1, 1. And then 1, 1 in binary is 3. And that's also 0 mod 3, so we're back at Q0. We read in another 0, that brings us up to 6, still 0 mod 3, so it's still at Q0. Then we read in our 1, and that brings us to 13, and 13 is 1 mod 3, so that brings us to state Q1. And then to top it all off, we have our final 1, and that brings us back to 27. And then 27 is 0 mod 3, so we land at state Q0. So what might be interesting now is, since we want to come up with some sort of transition function, we have to really look very closely at one specific transition over here. And then if we can inspect exactly what's happening in one specific transition, maybe we can piece together some notion of how this mod should change when we're appending a character to the string that we've already read. So what I'm going to do is I'm just going to focus on these two strings over here. So this 1101 and this 11011. And then we're going to try to figure out exactly what's happening between these two spots so we can try to come up with some sort of transition function that'll totally encompass all possible mods and all possible numbers that we're reading in. So after some weird arrow transitions over there, we have these two different things, one on top, one on bottom. And let's see exactly what the individual steps are to get from this thing over here to this thing over here. So, if we have this DFA that's read in 1101 so far, and our next character that we're reading in is this 1, the first thing we need to do is just kind of intuitively, we have to make space for this 1 to slot in at the end of our string. So what I'm going to do is I'm just going to take this 1101 and then just shift it to the left by 1. Well, if you know what a bit shift is, that's exactly what I'm doing. We're just taking this and we're shifting it to the left, and that leaves us an empty space here, which is a 0. So this 1101 turns into 11010. And then, if any of you are also familiar with what bit shift is, you will recognize that a bit shift by 1, by left, is basically equivalent to just multiplying it by 2. And an intuitive way to kind of think of this is if you're in base 10 and you have some number like 123 or 123, and then you add a 0 to the end of that, you get 1230. And that's equivalent to just multiplying by 10. But since we're dealing with base 2, when we add a 0, that's the equivalent of multiplying by 2. So here, you can see we have this turn into here, and then we have 13 turn into 26, since we multiplied by 2. And then now that we have this empty space open, we can just take this 1 that we're reading in and just add it to our new 11010. And that gives us this thing over here. So yeah, so our second step is going to be adding the character that we read. So in this case, we add 1, which gives us 26 plus 1 and 11010 plus 1. And then when we actually evaluate this addition, we're going to get our final answer 11011 and 27. So hopefully this makes sense as to how we're dealing with this binary string and our actual value of the binary number. But what's really, really big-brained about this is that we can just take exactly the same operations that we did and do them on the mod instead. Because of mod rules, when we're multiplying the base number, where we're multiplying 13 by 2, we can just multiply the mod by 2, and that gives us the correct result. And when we're adding 1 to the mod, so for example, when we're doing 26 plus 1, we can just do 2 plus 1, and this will also give us exactly the same or correct result. Since 2 plus 1 is 3, and then 3 mod 3 is just going to be 0 mod 3 over here. So all we're doing here is, to our mod, we're first multiplying 1 by 2, that gives us 2 mod 3, then we're doing 2 plus 1, which gives us 3 mod 3, but that simplifies down to 0 mod 3 at the bottom. And that gives us Q0. So I would take a second now to just stop and make sure that you really understand each of the individual steps that we're doing in this slide. So let's start actually constructing the transition function. And we can do this by getting set up by saying that our DFA has already read in some string s, which is a string in base 2. And the string s has some value omega with that's congruent to some I mod 3. So for example, if our string s is 11011, then it would be have value 27, which is congruent to 0 mod 3. And since we know that omega is congruent to I mod 3, we can say that our DFA is currently in state Q of I. And so the next thing that we want to do is we want to read in some k, which is either 0 or 1, since we're reading in the next character. And the question we want to ask is, how do we transition to the next state, given a state qi and some character k that we're reading in? And to answer this, we should look back to the previous slide where we kind of took a look at what exactly the specific steps that we need are to get from 1101 to 11011. So we know that we can concatenate string s with some character k, and that gives us some sk. But then we also know that this value omega is transformed by 2 omega plus k. Since we're bit shifting s left by 1, and then we're adding k, that gives us 2 omega plus k. But then the really big brain thing that we have from last slide is that we can just do exactly the same thing, not only to omega, but also to our mod, which is I. So 2 omega plus k is congruent to just 2i plus k mod 3. So now what we have is we have some rule to change the mod of a string s after we read in some k. And this is really exciting because we can just take this and just directly write out our transition function, which is just going to be given some state q of I and some character k. All we need to do is take 2i plus k, and then of course you'd interpret it mod 3 since you only have q0, q1, q2, and then you would transition to that state. And because we know that 2i plus k does the correct thing to our mod given some character k, we can say that this transition function is probably correct. And if you want to formalize this, you can of course use induction and then prove this property entirely rigorously by inducting on the length of the string. So now that we have this transition function, I just want to go over the example one brief more time to make sure that you actually believe this. So we start off with epsilon, which is q0, then we read in R1, this turns into q of 2 times 0 plus 1, which gives us q of 1, then we go to 2 times 1 plus 1, that turns us back to q of 0, and so on and so forth until we arrive finally at this q0, which we accept on because q0 means we're 0 mod 3, and that's a multiple of 3. So if this doesn't make sense to you, be sure to stop now and go back and make sure that you fully understand why this transition function works. Because next, we're going to actually take this intuitive idea and then write down our 5-tuple of the DFA that will follow our transition function and then follow all of our states that I wrote out. So for our DFA, we of course start with our states, which is just going to be q0, q1, and q2, which we've talked about earlier. And this represents 0 mod 3, 1 mod 3, and then 2 mod 3. And then our alphabet is just 0 and 1, since it's just given to us before. Then from the previous slide, we can just rip this transition function over, and that gives us our q of 2i plus k that we talked about. And then the remaining two things are just our starting state and our accepting states. So somewhat misleadingly, I'm going to say that q0 is equal to q0, since we want to start on a 0 mod 3 state, since our empty string just represents 0. And then we also want to just accept this q0 state, or this q0 state, since we only want to accept things that are 0 mod 3, or multiples of 3, so that makes sense that we would put q0 inside f. So just to make this a little bit more visual, I've gone and drawn out a little drawing of this actual DFA, where all these lines are actually just applying these transition functions to qi and to the number that we're reading in. So just to finish off, I want to go over a final example just on this finished DFA so you can convince yourself that it's working. So we start off at q0, we can read 1, 1, then we read a 0, and then we read another 1, 1. And that brings us back to q0, and because it's in q0, we're going to accept. So I just want to leave off with two final questions. So the first one is, try to finish writing this actual proof up formally. So to do that, you're going to need to show that this property that we introduced earlier in the video actually is held by this transition function that we introduced. And then second, I want you to think about more generally, is 3 the only number that would work in this case? Can you take some other mod like mod 4, or can you also take some other base like base 10 or octal or hexadecimal? And with that, I'm just going to leave you off to think about these questions on your own.